Okay, so we can get started. Welcome to the first Lauritsen Lecture of this year. This lecture series commemorates Charles Lauritsen and Thomas Lauritsen, the father and the son. Both were distinguished nuclear physicists and a professor at Caltech. Charles Christian Lauritsen was born in Denmark. While working as an engineer for a radio company in St. Louis, he attended a lecture by Robert Millikan. Inspired, he moved to Pasadena with his wife, Ooguri, and their 2-year-old son, Thomas, and he became a graduate student at Caltech at the age of 34. Received his PhD just before the Great Depression and remained at Caltech for the rest of his life. At Caltech, he founded the golden age of nuclear physics, and his laboratory produced more than 100 PhDs. Willie Thaler, one of Charles' students and Nobel laureate, wrote in the National Academy biographical memoir for him that through his own work, through the work of the laboratory that he established, and through students and colleagues, he exercised a profound influence on nuclear physics and its application in astronomy over a span of 4 decades. By active and continuous engagement for 30 years as participant, advisor, and consultant in the national scientific defense effort, he contributed to the interplay between science and government that is so essential to both. Thomas Lauritsen was born in Denmark, also born in Denmark, 2 years before his parents immigrated with him to the United States. They moved to Pasadena when he was 10. He was associated with Caltech for 41 years as an undergraduate, graduate student, and faculty member. He was a pioneer in the study of nuclear reactions and contributed significantly to our understanding of how stars generate energy, how the chemical elements are formed, how the universe evolved. In the National Academy biographical memoir for him, again, Willie Thaler with Faye Attenberg wrote, the exhilarating, intense scientific work was complemented on many evenings and nights by continued interaction between faculty, students, and outside visitors, most often at Tom and Margie's house, over pots of spaghetti and cases of beer, accompanied by old and new Scandinavian drinking songs. The closeness of faculty and students and visitors at Kellogg have made it a unique and uniquely influential institution in nuclear physics and nuclear astrophysics. Actually, Margie Lauritsen was our neighbor on Roseville Street east of campus, and knowing her, I can imagine the vibrant and welcoming atmosphere that Tom and Margie created for the Caltech community. So it gives me a great pleasure to introduce today's speaker in this distinguished series of lectures, Professor Thaler. Professor Thaler received his PhD from Harvard in 2006 and was a fellow of the Millikan Institute at UC Berkeley before joining the MIT faculty in 2010. At MIT, he is a professor in the Center for Theoretical Physics and the founding director of the NSF Institute for Artificial Intelligence and Fundamental Interactions. Actually, looking at his CV, I noticed that he also went to the same high school as my daughter. Among many awards and honors, he has received the DOE Presidential Early Career Award, the Sloan Fellowship, the Simons Fellowship, and the Simons Investigator Award, and he is a fellow of American Physical Society. He also has received several teaching and mentoring awards from MIT, so we can expect a wonderful talk today. The title of his talk is Particle Physics Meets Machine Learning. Please. Okay.
Thanks very much, Hirosi. Thanks everyone for being here today. The last time I was here at Caltech was a decade ago, and I feel just as intimidated by Feynman up here in the corner as I did at that time. But the topic of my talk is quite different because I had a conversion and now I am an evangelist for machine learning as it applies to the sciences. And what I'm advocating for in this talk today is a kind of centaur science. Centaur, the mythical creature that is half human, half beast, and trying to explain why a similar kind of half-half has been influential in the work that I've been doing in particle physics. So it's typical in these type of talks about machine learning that you fire up DALL-E and generate an AI image related to the title of your talk. And so I was planning to do the same thing, having an AI image of a centaur. But then I actually was giving a similar talk at University of Wisconsin-Madison, and Kyle Kramer, who's also someone who's really excited about AI and physics, he sent me a New Yorker cartoon that I think does a better job than any AI-generated image at capturing the spirit of this talk. This is the centaur scale, okay? And so you can ask, which is the physicist and which is the machine learning, okay? But really what I'm trying to advocate today is that we need the right amount of force, okay? And that too much physics and we're missing out an opportunity in scientific discovery by not taking advantage of machine learning strategies. But too much machine learning and maybe we're not as connected as close as we could to fundamental principles. This idea of this kind of centaur is the basis for the institute that I direct, the Institute for Artificial Intelligence and Fundamental Interactions, that was launched in August of 2020, back in pandemic times, but bringing together people working in deep learning with a community of people like us who do deep thinking in the physical sciences and trying to gain a deeper understanding, both a deeper understanding of the universe, but also a deeper understanding of the nature of intelligence, both human intelligence and machine intelligence. And one of the things that we're proud of in the Boston area is having a spectacular track record of taking early career talent, in particular our I-5 postdoctoral fellows, and launching them into careers into this interdisciplinary space. They have gone into jobs in industry, gone into jobs in academia. They're really galvanizing innovation in this sector. And we've also been able to train through a summer school program a large number of junior researchers. So, for example, my students are here at our summer school last year at MIT. And this year we're having yet another event down the road at Harvard. And just to give you a sense of the growth of this area, when we started, we were struggling to fill kind of our 80 people who could come. And now we had 400 applicants to us. And so we had to turn away really talented people working in this interdisciplinary space. So when we talked about sorry about that. So when we talked about AI and physics together, back in 2020, people had no idea what we were really talking about. Let me switch to.
That's good.
Let me switch to a clicker that will actually move me forward. When we talked about working in this space, people say, what are you talking about? But last year, a kind of recognition for AI plus physics from Stockholm. Depending on your perspective, this was either a really exciting moment for the intersection of AI plus physics, or if you're a more traditionalist, it was kind of horrifying. The idea that computer scientists would get a physics Nobel Prize. We're actually going to come back to this picture. In particular, Boltzmann machines will come into the later part of my talk. I'll try to explain how that's relevant for particle physics. But what was exciting for me about this Nobel Prize is that it was emphasizing a different viewpoint on intelligence. Oftentimes we think about intelligence as being a biological phenomenon. This Nobel Prize is emphasizing that there's a type of learning that we can do through dynamical systems, which are, of course, familiar to us as physicists. The power of statistical reasoning, that behind all of AI really is statistics. And then with the Nobel Prize in Chemistry, of course, broad implications for scientific discovery. And AI has been used in some way, shape, or form for physics for many decades, and kind of emphasizing that in the kind of citation for the Nobel Prize, highlighting, for example, the role that is played at interpreting data from the Large Hadron Collider, which is related to my area of study. So the thing that I want to emphasize in this talk, so the take-home message is the following: that in this collision between high-energy physics or particle physics and machine learning or AI, here is what my current viewpoint is. So first, to meet the standards of scientific rigor and performance, we need to teach machines to think like a physicist. In the popular culture, we talk about AI as hallucinating. That is, of course, completely unacceptable if you're trying to do scientific discovery. And principles from physics, like symmetries, robustness to systematic effects, exactness guarantees if you're doing a theoretical calculation, or just kind of the machinery of statistical inference. We need to make sure that those are baked into the technology we use for when we use AI in physics. So this is probably, in this audience at least, not controversial. What is controversial is the counterpoint to this, which is that to fully capitalize on AI technologies, we need to teach physicists to think like a machine. And yeah, things get a lot more quiet when we tell physicists that they may need to think in a more computational language. Actually, computational complexity turns out to be a really interesting muse for me in my research, and thinking about how the algorithmic structure of problems has actually helped me in my own research. Reframing questions in the language of optimization or brute force search, or more generally algorithmic reasoning. These are also things that you need to bring to the table. And so in this talk, I'll give you one example each in these two different directions. But this idea of Centaur science, just the right amount of force, it's not unfamiliar to us. And in fact, for a long time, progress in computation and information theory, it's long been intertwined with progress in the physical sciences. If you just think about statistical mechanics, there's a framing of that in the language of information theory, or vice versa. And then, with quantum computers, this is emphasizing a different mechanism of computation based on a physics principle. And independent of whether we ever get a real quantum computer in terms of operationally, it's changed the way that we think about the phrasing of problems and thinking about the complexity of tasks to be solved. And so Centaur science has been with us for a while. I'm now going to show you how this has impacted my own research in particle physics. So I'm going to give you two case studies in Centaur science. I'll start off with a kind of particle physics and machine learning 101. And I could spend a whole talk kind of explaining this, but the punchline for the first part of the talk is deciphering collision debris requires statistical inference, and that's very well matched to a Centaur scientist approach. And then to kind of show you an example of statistical inference in practice, I'll try to explain why there's an alligator on the slide, but giving transformers a boost, this is Lorentz boosts, making sure that you have a machine learning architecture that understands space-time symmetries. And one can help machines think like a physicist by building known symmetries into machine learning architectures. And you're going to see a fascinating way that theoretical physics concepts play a role in actually figuring out how to embed symmetries into a neural network. And then the last part of this talk is QCD theory meets information theory. And when physicists think like a machine, we can translate thorny theoretical challenges into optimization problems. And it turns out that there's interesting lessons to learn by thinking a more information theoretic optimization approach to doing calculations in quantum chromodynamics that turns out to be kind of interesting and giving me insights into the nature of QCD that I wouldn't have otherwise had but for this research. Okay, so to start things off, let me just set the stage and remind you about particle physics, and also just remind you why particle physics is really at its heart an inference problem. So we often show this picture of the standard model of particle physics with the quarks in orange, the leptons in green, the force carriers in blue, and the Higgs boson at the center of the standard model giving masses to fundamental particles. And if you look at this pinwheel, you might think that these are objects that we have seen directly in some way, that we held these particles in our hand. But that's far from the case. Basically, only three particles can you really see directly, at least in the collider context: photons, electrons, and muons, particles that exclusively interact via electromagnetic interactions. And those are elementary particles that really do hit our detectors. But everything else in that pinwheel has to be inferred. So my specialty, and indeed what I talked about a decade ago in the same room, are quarks and gluons from quantum chromodynamics. And quarks and gluons cannot be seen directly. You can only infer their presence by the patterns that they leave in your detector. And in particular, quarks and gluons, because of the strong force, they bind into mesons and baryons, the most famous of those being protons and neutrons. And because of the confinement of quarks and gluons, you can't separate out those degrees of freedom. You only infer the existence of quarks and gluons by experimental data, either experimental data on the spectrum of composite states that you see, or experimental data on the sprays of radiation called jets that emerge from collisions. And then filling out the rest of this, some of these particles basically decay instantaneously. Top quarks, Higgs bosons, W and Z bosons, they disintegrate basically as fast as you make them. The tau lepton is something where maybe you could say that you've seen it, but really it also disintegrates into a spray of particles kind of before you have a chance to really positively ID them. And neutrinos are particularly annoying because, at least in the collider context, they just sail through your detector. So you have to infer their presence just by the absence of the energy that would have come from those neutrinos. And then, the inference goes even deeper than that. It's not like a detector that you can even see those things directly. You are actually seeing collision debris like this, where you have heterogeneous sensors, tracking detectors, electromagnetic and hadronic calorimetry, muon systems, you have to infer what the particles were from those hits. And then my own study of jets, these manifestations of quarks and gluons that appear in this collision debris as these orange cones here, they're manifestations of quarks and gluons. This is what happens when you take a high energy quark or gluon and let it shower and fragment to form these ions and kaons and protons. But I can't just look at one of these sprays and say, yes, that's a quark, that's a gluon. All I can do is do a statistical inference about the fraction of those jets that are probably quarks or probably gluons. And this inference task is particularly challenging because we have collisions every 25 nanoseconds at the LHC. And so colleagues of mine at MIT, in particular, Phil Harris, is someone who has been spending time thinking about how you do ultra-fast machine learning to be able to make decisions about collision debris using machine learning at the kind of, tens of or hundreds of nanosecond time scale. And so, these are my friends, these jets, these sprays of particles. Again, their jets are a manifestation of quarks and gluons, but they are not quarks and gluons themselves. And no jet carries actual information. You need a statistical ensemble of them. And so it's all about inference, inference, inference. And so while each of these event displays is quite pretty, it's the ensemble of them that you need to use to make decisions about the nature of the universe. And in particular, if you're looking for physics beyond the standard model, you have to say, are the patterns of jets that I see in the radiation, is it statistically more likely to come from predictions of the standard model or from some new physics scenario? So inference, inference, inference. And machine learning is a really great engine for inference, because machine learning allows you to take trusted simulations and use those to estimate quantities that are used for statistical inference, for example, likelihood ratios. So let me now transition from particle physics 101 to a machine learning 101. And a trick that's used all the time to try to do what's known as simulation-based inference. This is a case where I have simulated data sets of collisions, and I try to convert that into a function that I can use to draw inferences about the structure of the universe. There's this trick called the likelihood ratio trick, where many problems in particle physics can basically be reshaped in this form. So let me talk about the case of trying to say, is this a jet more likely coming from a gluon or from a quark? So let's say I have distribution P. This is the distribution of some features of the jet, if it were coming from a gluon. And in Q, that's if it were coming from a quark. And notice that these things are overlapping. That's my statement that any one jet doesn't tell me information about what it really is. I have to have an ensemble to be able to make an inference. And if I want to do inference, I want to know whether something is more likely than not, or more likely to be one category or another. I want to estimate this ratio of P over Q. But I'm doing this with simulation. So all I have is simulated samples, finite, of P and Q. And somehow I want to take those simulations and do inference from those simulations. So here's the trick. Machine learning says you can give me some nice learnable function with lots of parameters. These are neural networks. If I take that neural network, I'm going to do an optimization task on it. And a particular optimization task that I can do is take over the sample P, the log of F, and try to make the minus of that as small as possible, while simultaneously over the sample Q, making F minus 1 as small as possible. And if you open up a statistics textbook, they will tell you that if you do this optimization with perfectly trustable simulations and infinitely training data, the answer will be something that has statistical meaning. In particular, the minimization of that loss functional is the likelihood ratio that we're trying to achieve. And the actual value at the minimum is a statistical quantity called the Colbert-Leider divergence. And then we're off to the races and we can do our maximum likelihood inference. Now, for many of you in this audience, if you're anything like me, you're seeing this and your eyes are starting to glaze over and saying, oh God, I did not come to a physics colloquium in order to get a lecture about statistics. And part of my own kind of reluctance to engage with this literature was saying, geez, this doesn't feel very familiar. But actually, optimizing quantities with the letter L, that is something that we teach our students in physics how to do in classical mechanics. And this thing, as stated in the statistics nomenclature, is super familiar to us. This is literally just Lagrangian mechanics, right? It's just Lagrangian mechanics with a funny action. So instead of having time, I have this feature as X. My Lagrangian it has this funny form. It depends on statistical distributions P and Q with that log F and that F minus 1. This particular Lagrangian doesn't have any time derivatives. There are some interesting generalizations where you can really have dynamical phenomena. So the Euler Lagrange equation at this point doesn't have any f dots in it. But nevertheless, the extrema of this, dl by df, setting that equal to 0, you can probably do this in your head, setting this thing equal to 0, functional derivative, that is just p over q. And so actually, it turns out that a lot of the things that you would read about when you're looking at a machine learning textbook convert it to Lagrangian mechanics, and you kind of instantaneously derive interesting loss functions or implications. And it also changes your mindset. Instead of saying, I want to derive this quantity p over q, instead you say, let me specify a problem whose optimization gives me p over q. And that transition from specifying, so from solving problems to specifying problems, that's the transition that I went through, which made me, again, an evangelist for machine learning. So let's see what that transition looked like. So I was very much an AR curmudgeon. What I said at the beginning of the talk about deep learning and deep thinking, that started off as me complaining about my theory colleagues who were doing all this deep learning. I said, come on, we're theoretical physicists. What we really should be doing is deep thinking. Now the joke's on me that I'm advocating for a synthesis of those two things. And when our AI Institute was announced, Dennis Ooguri from the New York Times called me up and asked me the provocative question, can a computer devise a theory of everything? And to give you a sense of my thinking at the time, I was very much in evangelist mode. So let me just read the quote that's in the Times from November of 2020. So in 5 to 10 years from now, I'm going to want to do exactly what you're getting at, that is devise a theory of everything. Here's the data, here's a very rough toolkit, find the equation I could put on a t-shirt. The equation that replaces the standard model of particle physics. What's the equation that replaces Einstein's general relativity? Okay. And my friends made a ton of fun of me in November of 2020. They said, we're nowhere near having AI systems that have any reasoning capability whatsoever. And then 2 years later, ChatGPT came on the market. And then the question was the opposite. It's like, Jesse, why haven't you already figured out the equation that goes beyond the standard model? Don't you know that we have these language models that can parse through massive data sets and certainly could spit out the answer to life, the universe, and everything? And the reality is that there are people definitely pursuing this line of research, and it's actually something that I'm quite optimistic about. But in this intervening time, it's been very interesting to see actually what it looks like in practice when you try to take concepts from physics and concepts from machine learning and put them together. And it doesn't look like, yes, here's the equation that replaces things. It looks different. So let me just show you some examples of what it looks like when you try to do the synthesis. So a different colloquium that I would have given 3 years ago is coming back to this question of quarks and gluons and doing something that I just told you was impossible. I told you that there was no possible way of telling whether an individual quark or a gluon, like whether an individual jet had that property or another. And yet here I have a plot that separately separates out gluons and quarks and makes curves in solid that correspond to experimental data and curves in dash that correspond to a particular theoretical prediction. And behind the scenes here of disentangling quarks and gluons into their components, behind the scenes are 5 distinct machine learning techniques with cute little logos. And this is a type of plot that I would have no idea how to have done before I got involved in machine learning, but turns out to have very interesting implications when you're thinking about the notion of what a quark or a gluon is. So a quark or a gluon in quantum chromodynamics is a parton. A parton is like a zero-dimensional object, like a point. And so that's represented on this graph here at high energies, is that you have a point, 0 dimensions, if you're studying this data set at energy scale corresponding to the production of these jets. But then as you evolve down in scale, quarks and gluons carry color charge. They radiate more quarks and gluons. And the rate at which they radiate is proportional to how much charge they carry under the strong force. And that's shown here as these curves, this growth in dimensionality, kind of a like fractal-like structure, growing dimensionality, that corresponds to radiation coming from quantum chromodynamics. And then the fact that these things agree with theory is because it turns out that in data, if you do a set of machine learning strategies to separate out quarks and gluons in some statistical way, the ratio of color charge of quarks and gluons, which I actually explained a decade ago in this room, is 9/4. That is then shown here in the ratios between these 3 curves. But again, I wouldn't have had to do this without machine learning. It turns out that you need this whole suite of different techniques in order to expose this kind of emergent dimensionality of quarks and gluons. And for the experts, this running here, this is a data science version of an anomalous dimension. Actually, these curves, which again were applied without knowing anything about partons, quarks, and gluons directly, they turn out to be related to what's known as the cusp anomalous dimension. So that's an example of revisiting a concept from QCD, but revisiting through a machine learning lens. More recently, we've been trying to use machine learning to discover new phenomena. But before you discover new phenomena, you want to make sure you can discover old phenomena. So in QCD, you can have bound states between different types of quarks that have interesting features. In particular, if you take a bottom quark and an anti-bottom quark, put them together, that gives you what's known as an epsilon. And what we did is we took archival data from the CMS experiment, went into a region of phase space that without machine learning, you can't see any structures. The epsilons are known to be around 10 GeV in mass, but you don't see any structure in this blue curve. But then again, using a suite of machine learning techniques, some deep learning, some shallow learning. So the deep learning is something called normalizing flows. The shallow learning is something called boosted decision trees. You can actually have the machine dig out a signal, and you see these old known structures appearing in these curves as you make harder and harder cuts. You see this structure emerging. But even though you're using machine learning in order to unearth this hidden signal, the actual statistical significances, as stated in the number of sigmas of discovery, we needed physics domain knowledge about basically what resonances look like, that they are localized in phase space. And without that assumption, you actually aren't able to assign a rigorous statistical uncertainty, or a statistical significance rather. And also, it's also been interesting to see the way that machine learning allows you to go beyond some of the techniques that we've done in the past. So the so-called cut and count method has a certain level of significance, which you can boost using that likelihood trick that I told you about earlier. So behind the scenes, these plots look very familiar to people who've been to particle physics talks, but behind the scenes, there's a lot of machine learning being used. And so this gives rise, as I was saying, to the Centaur scientists who are synthesizing physics intelligence and artificial intelligence. And we're not really abandoning both, we're taking advantage of the complementary strengths of both approaches. And that's what I'm going to be showing you more of in these case studies for the rest of this talk. Okay, so what we're going to do next is we're going to talk about, okay, how can you actually take a concept like Lorentz symmetry and bake it into a neural network? And this is an interesting project because this is a project in collaboration with academics at University of Heidelberg, but also with folks from industry, from Qualcomm AI. And you ask, why did Qualcomm care about Lorentz boosts? Well, Qualcomm cares about embedding symmetries into neural networks because when you embed symmetries into neural networks, you're able to use less training data than you would otherwise if you didn't have that symmetry prior. So that's why they're interested in this type of collaboration. And it's interesting to see the kind of mashup that you get. And as I said, there's at least one Easter egg for the theoretical physicist in this audience about how we actually accomplished this mashup. So let me just remind you, so what I've already told you about the LHC analysis pipeline is that it's all about inference. And the way you do it, you take real data, put it through a pipeline, make synthetic data based on quantum field theory, put it through the same pipeline, you do that comparison with simulation-based inference. And this pipeline has existed for decades. And shallow machine learning, low-dimensional statistics, they have a long history in high-energy physics. The new thing that we're doing are deep learning and high-dimensional statistics, where we're taking advantage of more features in our data set. So kind of philosophically, it's quite similar to what's been done in the past, but being able to efficiently process high-dimensional data sets, that's new. And what this really needs is vast data sets, both real data sets, but also trustable simulations. And if you didn't have trustable simulations, then what I'm talking about is an example of garbage in, garbage out. Okay, so this is what we have on the high-energy physics side in this collision. On the machine learning side, the juggernaut in the AI world right now are transformers. And let me try to not describe really what a transformer is or what these diagrams are, but try to explain it maybe more conceptually what a transformer is trying to accomplish. So if you remember from this likelihood ratio trick, you just need to have some flexible function that can be used to optimize to minimize some loss function. Okay, at that level, every neural network is just some kind of fancy function approximation. And depending on how fancy that function is, that function could do a good or bad job of learning the dynamics that you're interested in. So the classic feed-forward neural network is based on linear transformations and nonlinear activations. And that's certainly inside of these transformers. You can see these kind of feed-forward layers in there. But the star of the show for transformers is this thing that's called attention, And attention is something that I can explain in two different ways. So one way of explaining attention is in the context of visual signal processing. You want to pay attention to a particular part of a visual scene. That means you want to mask out things you don't care about and focus on the things you do care about. Okay, that's one way of talking about what attention is. Another way of talking about attention is that attention is just multiplication. That things you don't care about, you multiply by 0, things you care about, you multiply by 1. And multiplication is kind of an important primitive operation that we experience all the time in physics, or the generalization of multiplication in terms of inner and outer products that appears everywhere. And so it's maybe not so surprising that if you have something with this attention mechanism that has multiplication as a primary, that you can do a better job than you could if you didn't have that operation. And the particular type of attention, this so-called dot product attention, is one when I ask machine learning experts why this form of multiplication and not some other form of multiplication. They'll just say, well, it scales well empirically, and indeed in ChatGPT, the T of GPT is transformer, and it's obviously taken over the world a bit. But there's also other ways of doing multiplication. And so, for example, with my student Rika Gambhir and Bowdoin undergraduate Athis Osapatan, we've introduced other types of multiplication structures that indeed give you better performance than if you just had linear transformations and nonlinear activations. So this is the insight that you have from the machine learning side. And now we want to put these things together, take the symmetry structures of physics, put them together with transformers. That's our goal. So let me just say a little bit more about transformers. Probably the way that you've encountered transformers has been to fire up a large language model. And you've heard of ChatGPT, but if you haven't heard it already, you can get a digital version of me, ChatJessieT. And this was an April Fool's joke at my expense, which is a heavily prompt engineered version of ChatGPT, made by a number of troublemakers, but not using funds from the National Science Foundation. Important to emphasize that. And if you ask me or it what a transformer is, it will say, named after its ability to transform input sequences into output sequences, transformers have revolutionized the field with their attention mechanism, allowing them to weigh the importance of different words in a sentence when making predictions. Think of a transformer as the Einstein of language models, able to warp and bend words in ways that even make a particle physicist's head spin. So you can ask whether its description of transformers is better or not than the human version of me. But it's kind of fascinating, the ability of these language models to process textual information. And you can ask it or me about what the theory of everything is, and it will actually give you pretty interesting dialogue about the hierarchy problem in particle physics, about quantum gravity. It doesn't actually give a useful answer, but it's fun to interact with. And what we realized is that what was started off as an April Fool's joke would actually be a really great way of doing science communication. And so you can take a slightly more famous physicist than myself, Marie Curie, and you can prompt engineer to try to mimic her style of speech and her knowledge. And of course, her time was before the time of AI. So if you ask Marie Curie, why is it important to fund AI in science? Of course, she/it doesn't know that it exists. Nevertheless, and this is maybe particularly profound in our current moment in 2025, science is the key to understanding the world around us. It is through scientific research that we've been able to make significant advances in medicine, technology, and various other fields. In my own experience, it was through generous funding of our research that my husband Pierre and I were able to discover the elements polonium and radium. This discovery not only expanded our understanding of atomic structure and radioactivity, but also led to the developments in new treatments for cancer. And so you can imagine, people at the Cambridge Science Festival last year really had fun interacting with this chatbot, and this is an example of the outreach potential of language tools in the sciences. Another thing that you can do with transformers is to interact with data in a way that is quite dynamic. I don't know how to do this with particle physics data, but with one of our I5 fellows, Siddharth Mishra Sharma, and a Harvard undergraduate, Yiding Song, we were able to identify correlations in a data set of Hubble images, where the data set had images taken by the Hubble Space Telescope, and then side by side with that, the proposal abstracts to justify why you want to point that telescope at that part of the sky. And this is, again, a correlation between an image and a type of caption, but this caption is a noisy caption because maybe you point your telescope at that part of the sky and the thing that the scientists thought they wanted to see wouldn't be seen. But you can use transformers to identify this correlation. So what you do is you say, I take observations from Hubble, you take an image transformer, and you try to embed it into a high-dimensional space. You take the text from the proposal abstract, you put it into a text transformer, you also embed it into some high-dimensional space. And then you try to align these vectors for images and captions that come from the same observation, and try to push them apart in cases where they don't. So this is known as contrastive learning or contrastive language image pre-training. And then this gives you an abstract representation of this whole data set that then you can do queries of. And so one particular thing you can do is you can say, okay, I would look at this abstract space and I want to know what text and what images are close by and try to use that to do inference. So for example, I am not an astronomer. And so if you showed me this picture, what is this a picture of? I, as well as a kind of off-the-shelf transformer structure, would say, oh, that's an Einstein ring. Looks like a gravitational lens. Looks like a gravitational lens to me. I'm a particle physicist. Yeah, sure. And then when I see that something with fancy things here, vision transformers trained on the internet data, says that that's a gravitational lens, sure, I trust it. But of course, anyone who knows anything about astrophysics knows that that ring is kind of squashed. And also, if you know what part of the sky you're pointing at, that is definitely not a gravitational lens. And this was actually associated with a proposal abstract to look at supernova 1987A. And so actually, if you use this pre-training on the actual scientific data, you correctly identify that as being a supernova remnant. But this is an example of a way of interacting with data sets in new ways as facilitated by this amazingly powerful transformer architecture. So great, let's use transformers for particle physics. And of course, that's been done. It was done in 2022. Party, the particle transformer, it looks very similar to the diagram that I showed you before. But of course, the people who built this are physicists. And they noticed that an off-the-shelf transformer didn't actually do very well. So they introduced this little kind of trick, this U matrix, which actually secretly is just hard-coding physics knowledge in there. So they're basically trying to do the Centaur science approach. They're taking transformer, adding to it physics knowledge about the interactions of particles and using that to get better performance. But they're basically hard-coding this in a way that's not learnable. To really take advantage of the flexibility of AI with physics principles, we would like to teach the transformer physics, in particular, teach it some symmetries. And the symmetry that's highly relevant for studying jet physics is Lorentz boost, because if I have some object, let's say a W boson that decays to 2 quarks, and I perform a Lorentz transformation, basically relativistic beaming of those jets so that you have one fat jet with substructure in it, it's still the same W boson, it's still the same object. So you'd like to have this knowledge of the way that Lorentz transformations, even if the data set looks different, the inference should be the same. You'd like to bake that into a transformer. And have people done that? Of course, people have done that. There's various algorithms with funny names like Pelican and LorentzNet that have done exactly that. And what they're doing is they're preserving the symmetry structure. So what this equation here says is that if I'm trying to make an inference F on some jet V, and I do a Lorentz transformation on it, I should get the same answer as if I do the inference on the object and then do the Lorentz transformation afterwards. So this is known as equivariance to machine learning practitioners, or physicists would call it covariance. And if I want to interface this with a transformer, then I need to do this in a way that preserves multiplication. And all of us remember how to do multiplication, maybe not of Lorentz groups, but certainly in quantum mechanics, we learned how to do addition of angular momentum. And thinking about the horrors when I taught at MIT 806, which is the 3rd semester of quantum mechanics, and trying to explain to my students, Clutch-Gordon maps and things like that. Actually, I was in 805 in quantum mechanics too, and the students always groan when they see that. And imagine trying to build these tables into a transformer. Doesn't sound very fun, though. Of course, people have tried to do that. But can we do it in a similar way? Can we take advantage of other domain knowledge that we have in physics in order to do the synthesis in a more streamlined way? And the answer is yes. And here's now the Easter egg for theoretical physicists. The inspiration goes back to something that seems absolutely nothing to do with what I've talked about thus far. It goes back to a hypothetical symmetry, symmetry between bosons and fermions known as supersymmetry. So it's actually a course that I taught last semester. Usually people think about supersymmetry as a way of maybe solving a hierarchy problem in particle physics, but here we're going to use it as inspiration for how to build a machine learning architecture. So supersymmetry, as I said, is a hypothetical symmetry that relates bosons and fermions. But if you want to do actual calculations in supersymmetry, it's a real pain to treat the bosons and fermions separately. So the easiest way to do SUSY calculations, which is in this class that I taught last semester, is going in superspace. And superspace allows you to package together in one object, called a chiral superfield, package together bosons and fermions. And the way that you have things with different spin statistics and different Lorentz transformations coexist is you put placeholder fields, these placeholder coordinates, fermionic coordinates, superspace coordinates, that allow you to package bosons and fermions together. And once you've done that packaging, the superfield transforms like a boson, but it contains a fermion inside of it. You just have to be careful about that placeholder. And then once you have this thing, you can freely add, multiply them together, and you always come back to the same form, which means that if you build a transformer for superspace, we can just take these objects, drop them into the transformer, and automatically you would get the symmetry relations. So the trick is to introduce a placeholder with well-defined transformation properties. So you can do the same thing for some of the Lorentz group. So this is actually known. It's known as a geometric algebra. If you haven't heard that phrase before, it's something fun to look up. We need to figure out a suitable placeholder for the Lorentz group. What is something that allows us to keep track of Lorentz indices without actually having to keep track of Lorentz indices? And it's actually the gamma matrices from the Dirac equation that allows us to build a space-time algebra to package things together. So it works for some of the Lorentz representations, the ones that are most relevant for LHC physics: scalars, vectors, antisymmetric tensors, axial vectors, pseudoscalars. You can ask me during Q&A what happens to something like the stress energy tensor that's symmetric. And you package them together with gamma matrices, sigma, gamma fives, you get pseudoscalars. And it has totally well-defined multiplication rules. And this structure, basically anywhere you had a scalar in your transformer, just replace it with this object, and all the multiplication rules just follow. And so you just literally drop this into a transformer architecture, and you're off to the races. And again, a fascinating line of thought of thinking about what have we seen in physics that's worked in the past, namely superspace. Geometric algebra is really not so familiar to us, but something that machine learning folks are enamored in, and seeing this parallel is really quite interesting. And then the synthesis of these things together gives rise to this Lorentz equivariant geometric algebra transformer, otherwise known as alligator, which is why we have this green alligator as our logo. And the details of these plots don't matter. All you need to know is green is good. And so in various tasks relevant to the LHC, the green curve is always better than the other curves. And what's really fascinating, if you look at the evolution of, let's say, jet tagging, in this case, is top tagging, that there was different phases in the evolution of the field where you started off with incorporating certain types of symmetries. For example, the equivalence of identical particles from quantum mechanics. That's my work back in 2019. And then as you're starting to add more structure, in particular Lorentz symmetry, you're starting to get kind of state-of-the-art performance. Where now actually you are less asking questions about whether machine learning is relevant for these problems, but worrying that machine learning is doing too good of a job, and we actually need to worry about, for example, systematic uncertainties in our simulations. But hopefully this example gives you kind of an interesting way that we can get state-of-the-art results from the Centaur style merging of physical and computational structures. The physical structure of symmetries merged together with the computational structures of the attention mechanism. Okay, so this is maybe the direction that makes physicists feel happy. Great, I get symmetries and I bake them in. That makes me feel happy. The other direction of us trying to think like a machine makes us less happy. And depending on your perspective, you could be like really unhappy, so unhappy that you would even think that there's a danger to thinking like a machine. And so this was a position paper by David Hogg and Soledad Villar with the position, is machine learning good or bad for the natural sciences? Okay, so let me just read you the beginning of this abstract. Machine learning methods are having a huge impact across all the sciences. However, machine learning has a strong ontology in which only the data exists, and a strong epistemology in which a model is considered good if it performs well on held out training data. These philosophies are in strong conflict with both standard practices and key philosophies in the natural sciences. So I myself am not a philosopher of science, so I see the words ontology and epistemology and I get a little bit scared. But let me try to just unpack what this argument is in this paper that's simultaneously very inspiring and also quite infuriating. Maybe a Centaur style version of those two emotions. But here's roughly what it's saying. Machine learning, what exists is data. And what success looks like is accurate modeling of that data. So when you say I take data from the internet and I train a transformer to mimic the structures that I see on the internet, I declare success if I'm able to generate text that I would have expected to maybe read on the internet. And if I do conditional prompting, and I say, please give me expert opinions, it will use that part of the internet that actually has expert advice in it. So that's what we say in machine learning, just the data exists and success is accurately modeling that data. But in the natural sciences, in particular in physics, a lot of things exist that aren't data. You know, quantum field theory exists. Particles like quarks and gluons, we think of them as kind of existing, even though I just told you you can't see them directly, but we think of them as fields in our quantum field theories. Coupling constants, those exist. But they don't have a direct manifestation in terms of data, but nevertheless, we think of them as having physical significance. And success is not accurate modeling. In fact, we're very suspicious when we accurately model our data, and only do that, we want to have an understanding of what's going on. So it's not sufficient to just say, oh yes, I've mimicked my data in a useful way. We want to say that we actually understand the fundamental underpinnings of what's going on. So let me just highlight this, this tension here in the case of the LHC. So let's say I built a generative model. So this is a model that can generate synthetic data. I'm going to have synthetic data that mimics all the data that's being collected at the Large Hadron Collider. So every 25 nanoseconds, instead of colliding particles, every 25 nanoseconds, I hit shift enter, and I generate collisions. Okay, would that be a good thing to do? And according to Hogg and Millar, if I could generate synthetic LHC collisions that were indistinguishable from real LHC data, that would conflict with the epistemology of the natural sciences, that it doesn't actually have a notion of understanding. And people have jokingly suggested, collect all the data from the LHC, train a machine learning model to mimic it, and then actually just throw away the data. So that all you're left with is this synthetic surrogate. I think we would be horrified if that's the way that experimental data were used. We'd say that we haven't gained an understanding, and God forbid, we actually threw out the thing that we're spending so much money to collect. So this is bad. On the other hand, what if you could generate synthetic LHC collisions based entirely on first principles QCD calculations? What if I could take the structure of the standard model and predict to arbitrary accuracy where every single pi and k I'm in my collision? That would be declared as an amazing success. But we are nowhere near being able to do this. I mean, very, very, very far from it. And so you have this tension. We have this tension between what machine learning can do, which is actually, you can generate synthetic collisions inspired by real data. It will do mimicry without understanding. But our ability to do understanding is quite limited. And this is, again, a call to Centaur science. What if you could combine models of the LHC data, which could in fact be like completely hallucinated, for the full phase space, but then incorporate first principles predictions whenever they're available? Could we do that? And then you would say, well, at least you have a prediction in every region of phase space. It may not be trustable, but in regions where you've actually done the calculation, you would have something that would be useful. Okay? And this is the thing that I'll try to explain how we were able to achieve this kind of Centaur style merging. So as promised, I was going to bring back the Nobel Prize, and bringing back the Nobel Prize for Hinton's work on Boltzmann machines. Actually, Boltzmann himself did not win the Nobel Prize, which is interesting. Anyway, it's interesting to think about how Boltzmann machines operate. So this is a learning architecture that we're going to hijack for particle physics purposes. So a Boltzmann machine is a type of generative model that samples data according to a statistical distribution. So we have some kind of Ising model, a bunch of spins, and we want to sample the spins according to this Boltzmann factor. So we want to select configurations with low energy more often than high energy in a way that agrees with thermodynamics. And somehow, at particle physics, I'm not doing spin, so I need to do some modification to this. But one way of understanding what this Boltzmann factor is that in an information theory language, it's kind of a maximum entropy solution. It's kind of the most level of ignorance with one constraint. The constraint that the average energy of that system is fixed to some value, to some thermodynamic quantity. So in that language, the 1 over t, that's a Lagrange multiplier that imposes a constraint to get a certain average energy, but then otherwise the distribution is unconstrained. And then the learning here happens because I choose the energy. I change the weights and the biases of this Ising model. I choose those in order to make sure that the distribution that I get corresponds to some ensemble of interest. So we want to hijack this idea, hijack this Boltzmann idea, and we want to hijack this for particle physics. And in some sense, you get a literal Centaur in terms of the equation. So we have to go from spins to continuous phase space where all the different directions of the particles go. which means that you can't use regular entropy, which only works if you have countable things. When you have things that are continuous, you need to have some notion of relative entropy. So relative to what? Relative to a prior here. So by the color coding here, we have yellow for machine learning. This could be a completely hallucinated prior over phase space, maybe trained on LHC data, maybe coming from a Parton-Shower Monte Carlo model, but something that we aren't quite certain about, but our best guess, given the available information for the whole of phase space. And then we have a constrained quantity corresponding to someone's hard-fought calculation, where they have calculated some average quantity about collider physics proposed here with a Lagrange multiplier. And the beautiful thing about Boltzmann mechanics and information theory is that you can just add up all these different constraints and throw them in an exponent. And so we have like the Centaur, we have the human and the beast, or vice versa. You know, one that could be coming from a hallucination and one that's really coming from first principles knowledge. And they're literally, in this case, multiplied together to make an overall prediction. Okay, so this is something that I can do. And there was nothing actually stopping me, or really anyone, from doing this decades ago. It turns out that actually to solve these Lagrange multipliers, you do need machine learning tools like atom optimization to actually do this numerically. But this idea in maximum entropy, this is something that people have talked about in the field or other fields for a while, but people haven't applied it to QCD. But inspired in some ways by this Nobel Prize and inspired by some other things, we started looking around QCD literature and say, wait, do we actually have things that take this form? Do we have something that looks like something with an multiplied by an exponent? So now you can go to my calculations that I've done in the past and ask, okay, in QCD, do we have exponents? So some probability distribution, do we have exponents? Yes, we have an exponent. That one, ignore it. That's my domain knowledge. I have physics knowledge, maybe that particular exponent, don't focus on it. This exponent is super important. This is known in QCD or in QED for that matter as a Sudakov form factor. And this exponential structure is quite fascinating. So this R is called a radiator. It depends on the strong coupling constant. It depends on logarithms of observables. And if you ignore that B, that's more domain knowledge. You have something times log squared. And again, that exponential, that's really important. Okay? So if you're just a QCD theorist, you would look at that expression and say, yeah, I've seen that before. That's a simplified next to leading logarithmic calculation. Whatever, we do those all the time. You know, show me the formula for next to leading log. This is not interesting. And that's what a QCD theorist would say. A machine learning practitioner would look at this and say, ooh, we have Euler gammas and gamma functions. Ooh, I could do some kind of neurosymbolic learning to try to learn this data set. But to a Centaur scientist, conditioned on the previous slide where I told you that exponents are important, a Centaur scientist, namely me, would look at that exponent and say, oh my God, the Sudakov form factor, I'll just say these are just all jargon words. These mean a lot to me. Like, I was talking with Cliff earlier that sometimes you do science not necessarily for the understanding of other people, for the understanding of yourself. And so this next sentence like just makes my heart sing. Okay, so the Sudakov form factor is a kind of Boltzmann factor, but a custom anomalous dimension is like a Lagrange multiplier that enforces a constraint of the second logarithm moment of the distribution. Eureka. Okay, so let's unpack this a little bit. So Sudakov form factor, Boltzmann factor, we have an exponential. This prefactor here, that kind of looks like a temperature. In fact, there's even beta, happens to be in the denominator, not the numerator, but that's turns out to be something that's interesting, the cusp anomalous dimension, but to Boltzmann, that would be a Lagrange multiplier. And the thing that's being constrained is this L squared, enforcing a constraint on the average value of L squared. L is a log, the second logarithm moment of this distribution. And then, shockingly, despite this format, no one has ever computed in QCD the second logarithm moment, or even any logarithm moment of anything ever, which is shocking because after what I just told you, it's obvious that that's the thing that you care about. So over the course of the year, I was working on QCD experts, in particular, Ben Ossie, Kyle Lee, and Stefan Hertwig, trying to convince them, look, we have this Centaur style merging, and all you need to do is calculate a bunch of logarithm moments of some interesting collider observable. And finally, I convinced Kyle, here they are, done. We computed them for the first time, inspired by this structure. And then you can see the Centaur style approach manifest. So we start off with, okay, this happens to be a particular particle physics distribution called thrust. And in blue is the hallucinations. I guess the colors got backwards, sorry. Blue is the hallucinations. That corresponds to distributions that I don't really know about. I'm not sure if they're correct. And what I can do is by imposing these constraints, I can shrink it down to these yellow. And that yellow corresponds to improved knowledge. In fact, the more knowledge I put in there, I can get the error bars even smaller and smaller. And that you see kind of together this exceptionally good prediction to next to leading log accuracy plus alpha squared corrections for a particular event shape that's shown A plus A minus. And this type of accuracy is one that, otherwise without this method would be quite difficult to achieve. But then this is a prediction not just in 1D, but over the whole phase space. And over the whole phase space, you can now look at what things look like. So we can compare it to LEP data. We see spectacular agreement as you go to a higher accuracy. But then you also make predictions for other regions of phase space. And this is where you can actually use your physics domain knowledge to investigate to what degree the machine did a good job. So for observables here, which turn out to be correlated in terms of their theoretical structure to what we've already calculated, we see going from blue to orange, going from the hallucination to the constraint, we see a good collapse. Whereas this other observable here, which is not very well constrained, you see that the error bar does shrink, but doesn't shrink that much, which is a good thing. That says that if we haven't done the theory calculation, then the machine is not allowed to make a prediction in a place where I haven't actually given it appropriate first principles information. And this again, just to summarize, this Centaur science continued the tradition of relating properties of physical systems to concepts in computation and information theory. That information theory was the scaffolding that then taught us, and as someone who's worked on QCD for a while, what are the things that I should calculate? What are the things that actually I would need to inject in order to save ourselves from a machine learning hallucinating algorithm that might give us incorrect inference? Here I can tell you, actually even with error bars, how good I've done in terms of the theoretical calculation that I performed. Okay, so that's what I wanted to tell you about today. This Centaur science, and hopefully you've gotten a sense of the ways that we've been able to merge together these different areas. I gave you an example in the context of symmetries, and I gave you an example of how you can be inspired to do different types of theory calculations based on the ideas of optimization and information theory. And then just as the final advertisement for this AI Institute that I direct, that we're trying to do two things, thinking about AI as a pathway to scientific insight, but also the reverse, kind of physics intelligence as a pathway to AI innovation. So hopefully you got a little bit of a sense of both of those. But really progress in this interdisciplinary space are driven by early career talent. And it's a pleasure to be able to tell you about some of this work done by early career researchers that are pushing this Centaur science approach. Okay, thanks very much.
Thank you very much. We have time for questions. Okay.
Maybe that's a technical question. For the second part of your talk, where you're looking for ways to improve symmetry, so there is this set transformer architecture, which is very good at coding symmetries. Why didn't that work? Did you try it?
So for set-based approaches as opposed to transformers, yeah. So that was actually, so there's a whole backup slides. This is what a set-based architecture thinks jets look like, and this is super crazy. Of course, it's a different type of hallucinatory thing. Like, okay, what type of mushrooms do you take? So it's set-based. So you can think of what are permutation invariant objects. So permutation invariant objects are like sums. And now you need to do something that's symmetric. Therefore, you need to take each particle and you need to encode it in some latent space. And this is what this latent space looks like for QCD jets. And it works incredibly well. Not quite as well as transformers, but it works well in terms of performance, but also works well for visualization. And this particular structure, these rings correspond to where the machine is paying attention to. Not pay attention to in what I said with attention, but pay attention to in terms of kind of what regions are being emphasized. You can actually show, I don't have it on this slide deck, but you can show that the particular way that these rubber bands are going actually follows from the collinear singularity structure of QCD. So you actually rederive in a machine learning way the collinear singularity structure, and that's indeed what you get from these set-based approaches. Transformers are too complicated to look into the interior of. So I actually really like these set-based ones if your goal is interpretability. But we have used them, and it just doesn't quite have the same performance as these more advanced architecture.
Okay. Yes. Harv?
My question or comment is a little bit long. You didn't talk much about the nature of the scientific problem we face. There are a few facts. One is finding something beyond the standard model has probably resisted about 1 million man-years of effort so far. That alone. Discovery often takes multiple factors that we don't understand. So apart from a single surprise, there might be a synthesis of several surprises. For example, at the time of discovery of Quarkonia and the Large Hadron cross-section, there was color, there was the fourth quark flavor, and there was a bit of QCD. All surprises at once. And so it wasn't clear to me that if you can't wait for enough data and a high enough center of mass energy, whether any of these techniques are really targeting the kind of extremely speculative, how do I find the threads, in a domain which is truly at the edge. So you had several examples that show the problem. We run out of data, that's what the interesting stuff is. And when we see a disagreement, human beings immediately say, no problem, systematic errors cover the rest, like in slides 39 and 40.
Yeah.
So that's the problem.
Yeah.
I mean, describing the data better, doing calculations to higher order better, saving computational time, they're all useful, but they don't really attack the central problem of discovery before the next generation machine.
Yeah. So I have a couple things to say. So what you're talking about synthesis, kind of multimodal synthesis. Let's imagine this in the context of quantum mechanics. So let's say what you had were two things. You had the spectrum of hydrogen, and you had the black body spectrum. And that's all you had. So first of all, that would be amazing. You have confusing data. You have the the ultraviolet catastrophe somehow regulated, and then you have discrete energy levels of hydrogen. And so in that case, you at least saw something new. But then trying to figure out the meta theory, namely quantum mechanics, that synthesize those things together. One of the things that I wonder is how would we have, or how could you do that enabled by machine learning, where you really are looking at quite different modalities, and the underlying commonality of those is quite hidden from the raw data. This is related to what I was saying, that for us, the data by itself is not important, it's the underlying structures that we think are important. So that's one thing to say, and I do not know the answer, but that's one of the things that fascinates me when people who are super excited about saying, oh yes, machines are going to do all the science for us, saying, how actually could you, what is a machine encoding way of actually synthesizing information or surprising information from different or seemingly different data sets? Okay, then the other thing that you're pointing out is, like, unfortunately, we haven't even seen any deviations from the standard model, at least in collector data. And there, my thinking at the moment is, okay, are we sure that we have deployed all of the knowledge that we have about particle physics to date? Have we deployed that across the entirety of the LHC data set? And the answer is certainly no. And so this kind of exhaustive search approach, where I'm going to try to insert all the knowledge that I have and try to do a synthesis, and then try to look for deviations, that's my best guess. And so this last part of this talk, where I wrote down this formula, this particular formula, this is my best guess about what the standard model would be, having done as many of these constraint calculations as possible. And then you would then do some type of p-value study with the data and say, to what extent does my data agree or not with my best guess of the standard model, and crossing your fingers that you actually see some deviation beyond systematics. But the part of the reason why I myself have become really fascinated with just standard model predictions is that I do not know, unless we get super lucky and something screams at us, I do not know anything other than make the best span prediction of the standard model that I can and look for a deviation. I don't see another pathway with collider data. And even when I think about work that I've done on anomaly detection, even that's really anchored to how well do you know the standard model. And so this formula here is really a call to action to all those us who do precision calculations, to say, don't just do a precision calculation for one thing, find a synthesis of that information that you can really give to an experimentalist to look over the whole phase space for deviations. But it's not a very satisfying answer to your question, but also we're in this complicated situation of particle physics where indeed the challenges are one that I don't even know how to even start thinking about without machine learning. And even with machine learning, there's no guarantee that we'll make a discovery. well, it's not a discovery beyond the standard model. For me, I view this as a discovery for me personally of understanding something better about the structure of quantum field theory. But that may not be satisfying for someone who'd like to add a new entry to the particle data group book.
Joe, you have a question?
Well, I guess this is related to Harvey's question and the answer you just gave. The story of the second logarithmic moment, fascinating. But I didn't really follow to what extent and in what way your domain knowledge of QCD was going into the model, and you know what first principles QCD computation it was based on, and therefore to what extent we can interpret the success of the model as validating QCD.
Excellent. Okay, so it started off as a pattern matching exercise where we looked at these exponentials and say, oh yes, logarithm modes are important. And then you go and you say, okay, having done that pattern matching, you can ask the question, why haven't people who've studied QCD in the past, why didn't they notice this? And the answer is that if you follow that guy and you do order by order calculations in a Feynman diagrammatic expansion, logarithmic moments are ill-defined at every order. And so if you were doing this in the 1970s, you would be, or 80s, I guess, you would be laughed out of the room because someone would say what you have defined is not well defined in perturbation theory. It happened to be separately in a paper that I wrote, not with machine learning, this is before machine learning, in 2015 with Andrew Larkowski and Simona Marzani, that we realized that there were categories of observables that were not defined order by order in perturbation theory, but actually, if you did resummation, were defined. And then if you try to do an expansion in coupling, you find you get non-analytic behavior. You get like square roots of alpha s appearing.
That's kind of the whole Sudakov story, isn't it?
That is, and Sudakov safety is what I gave a chalk talk about a decade ago here, trying to explain that. So then Sudakov form factors, they give you log normal distributions. If you have a log normal distribution, of course, you characterize it by its mean invariance, but in log space. So it's kind of obvious in retrospect, this is what you should have done. But no one had done this calculation, in part because they didn't think you could do it order by order perturbation theory. And also, they didn't understand the point of it. And now I can say more confidently that what a fixed order calculation does from an information theoretic perspective, it calculates moments of ordinary observables. What recent calculations do uniquely is calculate moments of logarithmic observables. And this actually has interesting relationships to things that people talk about in statistics, where there's famous distributions like the Cauchy distribution that don't have any moments. And oftentimes this is viewed as kind of like a curiosity, they don't have moments. But then this language forces you to think about, even if something doesn't have regular moments, how do you characterize that distribution? And in this particular case, it happens to be logarithmic moments, other ways that you actually characterize the knowledge that you gain from a resum calculation. So it's not a linear, I took my physics domain knowledge and I pushed it into AI. It was the other way around. I thought like a machine. The machine or Boltzmann machines are telling me a given way of thinking. This breaks my brain about how I'm supposed to do my calculation. And then I have to reverse engineer a story to explain why this is the right approach. And so it's the other way. It's the thinking like a machine aspect of it. And then I've learned something by thinking about language that I didn't know before. And then I can synthesize it.
QCD calculation, the next to next cleaning order.
At the end of the day, this applies that.
Do because of the way you model it.
But at the end of the day, that's right.
Different comment. I was very disappointed when you showed the thrust. Let me explain. Can you put up there was one of the things we struggled with in the 1980s. Look, when you use thrust, then as it approaches 0.7, you have like the transition of 3 equal jets.
Yeah.
And it's unstable, and it's known to be unstable.
Yeah.
And you'll notice that your technique fails.
Yeah.
But human beings inject knowledge, not the kind of knowledge you say, but other knowledge. It's the same thing at a thrust of 1. You see how it, So what's going on? It's experimental physics knowledge. It is, for example, the granularity of the detector and how that affects thrust near 1. It's the details of the reconstruction in the detector, how the instability takes hold and how often it goes to the wrong one. And so it's not theoretical, it is knowledge, it's human knowledge.
So human knowledge is represented in the black curves. The black curves have the systematics, those are the experimental results.
That's
right. So actually,
I want to grapple with those things. So it's experimental physics, it's other external knowledge than theoretical physics knowledge.
By the way, 100% agree, and I'm working with people with archival Aleph data to take some of these machine learning techniques and actually redo this distribution. So for here, this is a story about doing a theory calculation. But I can tell you that
That was shocking because we had such advanced techniques and suddenly you revisit a problem which we dealt with in the early 1980s. And what we did about exactly those, the ends of that distribution.
So, right, there's a difference between what one does with the experimental data and actually what one does on the theory side. And actually, those two regions of phase space turn out to be particularly interesting ones from this perspective. So this region of phase space, you can actually see that our error bars, our theory error bars grow. And the reason is because we added this theory systematic, and error bars on the theory systematic for something that's called Sudakov-Shoulder resummation. Which was not actually incorporated into previous analyses of this left data set. So that's actually an additional feature that we're adding, actually blowing up our uncertainties to account for some of our theoretical mismodeling. And then actually, the fact that this is shown in linear space and not log space, that's also something that we learned. So a lot of the issues here, when we revisited the Aleph data in logarithmic space, the experimental data, we actually are learning some very interesting things about the way that reconstruction happens in that region of phase space. So you have this like giant thing on this log scale, like huge peak there. But once you spread this out into logarithmic space, you actually start to see some of the subtleties of the thrust reconstruction. Right. And so, the story that I told in this part of the talk was definitely a theory one. On the experimental side, because it's kind of equally interesting, and I could tell you a story about kind of multidimensional unfolding. That's kind of an interesting approach to trying to think about uncertainties in this particular type of data set, where we're trying to get away from some of the theory priors that were needed for unfolding in the past and try to do more robust unfolding that's actually taking advantage of more experimental information than was available back in the lab era.
Okay, yes.
Hi, yeah, thanks for the nice talk. I was trying to understand the takeaway from this. Like, can we actually use like this post-fit values to improve like our Pythia tunes, for example, or is it more just reweighting our?
So at the end of the day, if you want to know what in practice what this means, you run your existing analysis pipeline with Pythia, as you said, run through your JANT simulation, and then you phone up the theorist and say, hey, theorist, how many moments have you calculated thus far? And I'll say, okay, well, I've calculated 20 moments or 10 moments. Say, great, please give me your best reweighting. And then I do that reweighting. And then you go back 5 years later and say, how many moments have you calculated? Like, well, now I'm up to 2,000. And then I just give you new weights with uncertainties. And so actually, in terms of the propagation of theory information into the experimental pipeline, it becomes way simpler. Because all you do is take your existing full phase space information, and all I do is I just give you weights. So actually, from a kind of computational, or the organization of computational perspective, this is actually quite nice because it allows you to use information without having to generate, for example, new Monte Carlo samples. And for those of you who are familiar with the terms of Partland-Schauer matrix element matching, like normally every time you do a new Partland-Schauer matrix element match, you have to like run a new simulation. Here, no, I just take all that encoded into a weight factor, and then the only question is the variance of those weights. Once I get too big, that I might be inefficient in my sampling. But it's a different way of packaging theory information, and it puts the onus on us as theorists to provide our best guess with uncertainties. And now these uncertainties are a lot easier to, basically theorists can't hide anymore. Theorists used to say, oh yes, uncertainties are really tough because I have to model the whole distribution. Now I say, no, I have a finite number of moments, and come on, if you do 200 moments, you can do a 200 by 200 covariance matrix. And so we theorists can't hide anymore and actually have to put error bars on our calculations. But at the practical level, it's just I can't do event rates and drop the races.
Okay, no more questions? Okay, before we thank Jesse, I'd like to point out there will be a wine and cheese reception downstairs, so you're all welcome to join us. So thank you very much.